Hi everyone, welcome to our video on implicit differentiation. So implicit differentiation is used when we are trying to find the derivative of an equation. So when you have equals just any expression, so an equation just means you have equals in it. So like number 1 here down below, that's an equation. So that's near the bottom. So is this one, the y cubed equals x. That's an equation. And it's pretty nice. So implicit differentiation is different than our differentiation we've been doing so far, because we've been doing explicit differentiation, which means that we have y equals some x expression. Okay, so with these, you don't have to have y equals an x expression. You can have y's all over the place. Like again, in number 1, you have multiple y's. All right, the rules all still apply. It's all the same rules, and we'll still do it term by term. All right, so let's show the connection with something that we could do both ways. So find dy dx if y cubed equals x by solving for y first. All right, so they just want us to solve for y first in this problem, and then afterwards we would do our derivative. Well, to get y by itself first, we would cube root both sides. That way the cube root and the cube would cancel, and we would have y equals the cube root of x. Let's go ahead and just change that to x to the 1/3. Okay, so this is y equals an x expression. So this, let's go ahead and make that note. Y equals x expression means we would do the derivative. We do the derivative, explicitly. Okay, and that's like what we have been doing. So we have been doing it. We've been doing it. We just haven't really said that word ever, I don't think. So it's just the main way that we do derivatives. Okay, so anyway, so to do this derivative, we'll show it in blue, our one-step derivative. It would be dy dx equals, and then here we could just do the power rule. 1/3 comes to the front. X minus 1 from that power would give us negative 2/3. All right, and then that's it. And if we need to change it into a positive power, we could. So dy dx is 1/3 x to the 2/3, like that. And if they said, hey, change it back to a square root, you could even do that. Okay, so I'm just going to leave these all to the side here. So 1/3, and then x to the 2/3 would be the cube root of x squared. Okay, so these three are all the answer, just written in different forms. All right, so that's just using the power rule. All right, so let's show this problem using implicit differentiation. So that means I have my y cubed equals x by itself first, like this. All right, so implicit differentiation, so let's show it in blue that we're doing the derivative. So we are going to do the derivative in this step. So the only difference is we're going to do the derivative of y cubed just using the power rule, like normal. So it'd be 3y squared. So that's using the power rule. However, the only thing we have to do to make sure that we are doing it correctly is the second we do a derivative of a y term, just attach dy dx. Okay, so as soon as we do the derivative of a y part, attach dy dx. So that's the main difference. Okay, so derivative of a y term, ... make sure to attach dy dx. Okay, because so what we're saying is we just did the derivative of y right there with respect to x. So we still are doing it with respect to x. Okay, and then equal to the derivative of x would be 1, like that. And that's it. And we usually don't show anything afterwards. You could, I'm going to erase this in just a second, but we could say we just did the derivative of x with respect to x. So the derivative of x with respect to x, but at this point we treat this like a fraction. Dx divided by dx is 1, and that would just cancel out. So that would just go away anyway. Okay, so we never need to show it when we do it with x, because we know we're doing it with respect to x already. All right, and then all I want to do is solve for dy dx now. So at this point, we solve for dy dx. So it's treated like a big variable, like a big old x. And so to solve for it, all I would want to do is divide by 3y squared. Just like that. That's all it takes. And then now we've got our dy dx. So our dy dx is now by itself equal to 1 over 3y squared. And that's that. Okay, so we found it. So we've got our answer here. Okay, and then you might say, hey, but look at the ones we have boxed from the first one and look at this boxed one. They look different. I mean, the 1 over 3 is equivalent. Those are all the same. But I have y squared versus x to the 2/3, or x squared under a cube root. Well, if we go back to this, let's highlight that guy in pink. If we say, hey, y is the same thing as x to the 1/3, if I change that, so this is optional, I just want to show that they are the same. If we rewrite that, we would be able to show dy dx is 1 over 3, and then y, so in the highlight, y is the same as x to the 1/3, x to the 1/3, but it's still being squared. And then I know, hey, squaring and the 1/3 power would multiply, so this is the same as 1 over 3 x to the 2/3. And so that matches this middle one. So we can show, hey, yeah, they are the same. This that I boxed in blue does match those three. It's just shown differently. Okay, so that is implicit differentiation, though. So the main thing is just make sure to attach dy dx for every term that does a derivative with y. Okay, so let's do one more in this video where I've got find dy dx using implicit differentiation. Okay, so we have, let me just go ahead and write it. So nothing's happened yet. I just wanted to write it bigger. Okay, and then most of the time implicit differentiation is ready to go. So I don't have to do much. I can just jump straight into it. So we're doing the derivative at this point. The derivative of x is 1. And then we have plus. The derivative of y squared is use the power rule. You get 2y. And then just make sure again, hey, you just did a derivative of a y term. So attach dy dx. And then equal to the derivative of y cubed, power rule, would be 3y squared. And again, just make sure to attach dy dx. Now, this is where the implicit differentiation usually gets a little tough. So the derivative portion's done. Now, all I need to continue doing is solve for dy dx. And to do that, we often want to get them together on the same side. Okay, so that means I would want to subtract. Let's go ahead and subtract this 2y dy dx over to the other side so that I have 1 by itself equal to the 3y squared dy dx minus 2y dy dx. And let me put those in parentheses. The dy dx again is treated like a big old x. I want to solve for that. I want to get it by itself. All right, so when we have multiple dy dx's, we want them on the same side. Okay, so solve for dy dx. If we have multiple dy dx terms, we get them on the same side. Get on same side, and then factor. Okay, so this in the red, I could factor. Let's just put it, so maybe I shouldn't have rewritten that. I'm going to run out of room. Okay, so I'm factoring it out, though. So I'm factoring dy dx, which means 3y squared is left over in the first term, minus 2y is left over in the second term, equal to 1. And so if I want dy dx completely by itself, well, I have dy dx times something. So that means this times something should just get divided on over. Okay, and I'm just going to show with like blank parentheses here. So this, well, actually, let me squeeze it in. I'll try to squeeze it in. So sorry, the 3y squared minus 2y. Okay, so very poorly planned. Sorry. So I am dividing this over to both sides. And we're just going to clean it up. 3y squared minus 2y. Okay, and that way my dy dx is by itself. So those just canceled, and I'm left with 1 divided by that 3y squared minus 2y. Okay, so let's rewrite it right here. So my dy dx is solved for equals that 1 in the numerator divided by this expression that we divided over. So the 3y squared minus 2y. And that's that. Okay, so that's implicit differentiation. So we'll just do a bunch more examples in the next video. But for now, that's it. So thanks for watching, and I will see you next time.